A new quantum computer by Xanadu has solved in under 2 minutes a problem that would take the world's fastest supercomputer over 7 million years to work out. The key? It uses light for quantum computation, and since photons don't feel heat, it can run at room temperature, powering the first quantum data center. I've spent the last decade designing computer chips.
Get over it.
And I'm particularly excited about this milestone because this is the beginning of quantum data centers becoming a reality. Let me explain. Over the past few years, we witnessed an incredible AI revolution, which has been driven by GPUs and AI chips. In fact, the demand for computing power has never been higher. Meanwhile, the scaling of classical computer chips has slowed, and its performance has also grown slowly, linearly from year to year. But how do we get to exponential improvement? While probabilistic computers are still in the making, quantum computers are getting closer and closer to prime time, and they can deliver this exponential improvement. Just to give you a sense of the magnitude of what's possible, this new quantum chip from Xanadu that we will break down today has already achieved quantum supremacy. It performed Gaussian boson sampling in under 2 minutes, which would take a classical supercomputer over 7 million years to complete. You see, the speed-ups that we can achieve with quantum computing is truly remarkable for certain tasks. But the potential of this approach is enormous. And the reason behind is light. This new quantum processor is using light, so photons, instead of electrons or trapped ions for quantum computation. But why light? Well, we know that there is a plethora of great ways to build a qubit. One of the most common ways is superconducting qubit, the approach which pursued by tech giants like Google, IBM, and Amazon. The main challenge of this technology is that these qubits are extremely sensitive to noise. Anything, heat, vibration, cosmic rays, literally anything can throw their calculations off. Its operation requires temperatures colder than those found in deep space. And this is how a quantum computer used to look like. Isolated from the rest of the universe, placed inside a huge refrigerator. Now, just think about it. If every dozen of qubits requires such a massive cooling system, scaling it to a data center with 1 million qubits becomes nearly impossible, let alone building pocket-sized quantum devices. This is how it used to look like, but not anymore, because when we use light for quantum computing, we don't need these bulky cooling systems. In fact, photons don't interact much, and they don't feel heat. So this makes them way more stable, and this first property alone makes photonic quantum computers way easier to scale. Well, that's one aspect to this, but in fact the main advantage of using light for quantum computing is in networking. Just think about it. If we compute in light domain, we can stay in the same domain and use it to link many quantum systems together into one large quantum cluster. And we can do so using already existing communication infrastructure, fiber optics, that brings internet to every home. This means we can naturally link many quantum computer clusters together. Think about large AI data centers currently running on NVIDIA GPUs, but instead running quantum computation. This is where photonic quantum chips truly shine. Now, before we can even begin to talk about applications here, first of all, let's understand the fundamentals of photonic quantum computation. Here we deal with photons, tiny particles of light. It's in fact the smallest possible unit, or if you will, quantum, of electromagnetic energy. And photons have this beautiful feature called wave-particle duality. On one side, they behave like particles, which makes them very quantum. On the other side, their wave-like behavior makes them more similar with classical, so non-quantum systems, especially when we encode information using waves. Interestingly, there are several companies pursuing photonic quantum computing, and the classical way to build a photonic qubit is based on a single photon. In contrast, the Canadian startup Xanadu is using multiple photons here, and this makes the difference. It turns out, if you work with single photons, it becomes much more quantum, more random, more probabilistic. On the other hand, the more photons you use, the more it becomes a classical system, while still maintaining its quantum properties. Why does it matter? Because when you work with a classical single photon, you get a superposition of 0 and 1, so this classical quantum bit, right? But when you use multiple photons, you can create more complex states. And this gives you more flexibility and more power in how you can process quantum information. The states they work with start as a superposition of 0, 2, 4, and so on, only even numbers, and in theory this can go all the way to infinity, but of course in practice there is a physical energy cutoff. And this approach opens the door to a whole new class of tasks it can handle, like Gaussian boson sampling and others, including quantum chemistry. Now we understood how a photonic quantum bit is built, now let's understand how a photonic quantum processor works. And here we will start with a photonic core all the way up to a quantum data center. It starts with a single laser that generates a stream of light pulses, where each pulse represents a qubit. Then the light goes through this tiny circle called the ring resonator, which creates a quantum state, so-called squeezed state, which is Xanadu's version of the qubit. And then the light travels further, passing through beam splitters. You see here the first two rows. It actually combines the two beams together, allowing their quantum wave function to interfere, and at this point the qubits interact. And now, at the output, we have an entangled state. And then there is a third beam splitter, which is now mixing rows 2 and 3. So essentially, we are trying to get as many combinations as possible by mixing all 4 states together. Eventually, at the output, we have all 4 states entangled. And you may ask, well, where the computations are performed? Because typically it's done using quantum gates. But for Xanadu chip, it happens actually at the end, where the measurements are performed. Basically here, measurements induce the effect of the gates. So at the end, they perform a series of measurements using photodetectors, and these photodetectors count how many photons arrive, usually up to 7 or 8. And they measure all the outputs except one, and it has to be done with a very high precision to stay on the bright side of uncertainty. What's interesting here, even though you know with how many photons you started with, after entanglement and interference you don't know where each photon will end up. So the final measurement collapses the quantum state into one possible outcome, and this is known as projective measurement. And this is not only efficient, but also highly scalable approach, because photonic quantum computers naturally integrate with optical fiber, so they can naturally and easily connect many of quantum processors to solve larger, more complex tasks together, eventually building a quantum data center. And Xanadu did it. They proved it's possible. We will dive deep into details of this and implications just in a moment, but I find this progress very exciting. Let me know what you think in the comments, and if you enjoyed this episode, make sure to subscribe to the channel to stay up to date with what is next in technology. Now, before we dive into the quantum data centers, have you noticed something new? I finally upgraded my chair. I moved on from my old chair to a new ergonomic chair from Sihu, and I love it. You know, I work in sprints, sometimes 12 plus hours straight, and having a proper setup and posture is so important for how you feel, your health and productivity, and this chair made a huge difference. It's very comfortable for the back, for your arms, and especially for the lower back. It has self-adaptive lumbar support that moves with you, so you're always supported. The backrest and the wide headrest adjust to your posture, while for the armrests keep your arms relaxed. What I personally like the most about it is this waterfall-shaped seat, which makes you feel weightless, kind of floating. And this is definitely the most advanced and thought-through chair I've ever seen or tried. And of course, you know me, I care about aesthetics a lot. And I love the design of this chair because it's well built from top quality materials and it's a minimalistic design that just fits. To be honest, this chair has just one downside. Everyone in the house wants it, so I might need this second one. If you've been thinking about leveling up your work setup or home studio, highly recommend you to check out the Doro C300 chair from Sihu. Check it out through the link below and use my code, which you can see now on the screen, to get 6% off. Thank you, Sihu, for sponsoring this episode and for making my work days better. Now, just a few days ago, Xanadu announced their new Aurora quantum computer. Fun fact, the Aurora quantum computer is powered by the Borealis processor. You know Aurora Borealis, the stunning northern lights, which I hope to get a chance to see one day. For now, it links 4 photonic server racks in one system using only fiber optics and running at room temperature. At the moment, it features 84 squeeze-state qubits across 4 racks. Here, one rack handles the lasers and the rest handle the quantum processing. And here, I was lucky to get a chance to talk to the Dr. Christian Widbrook, the founder and CEO at Xanadu, about this huge achievement.
As the paper was published in Nature, and the team really did a world first here, where they created a modular, scalable, and network quantum computer. So modular because you've got individual server racks. They're just individual quantum computers. Scalable because we could go up to thousands of server racks today. And network, you can kind of see in the picture of the Aurora, there's yellow cable that's running through, and that's fiber optics where the light is traveling. It goes through a few different stages from top to bottom. But down the bottom, they're also connected to each other using the yellow cables as well, the photons. And so no one has done that before. So very proud moment for the team.
I mentioned that photonic quantum computers doesn't require cooling. However, in this system, they still do cool like 10% of the components, the part where the qubits are measured. Anticipating your questions, there is nothing fundamental that requires cooling here. But those photodetectors, the most advanced photodetectors they're using, they do require cool temperature to operate, because the colder you get, the better the accuracy will be. For now, roughly 10% of this quantum data center is cooled, while remaining 90% operates at room temperature. This means no cryogenic, no laser cooling, nothing. And this, of course, significantly reduces the complexity and the size of it. And that's a huge benefit for scaling it to a larger data center. Here, one very important benefit of computing with light comes in handy, because we are remaining in the light domain. So we are computing in the light domain, and then here we can share the entanglement across the larger system, across the data center. And this doesn't require any conversion, it's frictionless as long as we stay in the light domain. While in other approaches, take superconducting qubit for example, or any other flavor of qubit, they use non-photonic medium for computation, so atoms or electrons, and then they need to convert it to photons to share the information between different cryogenic crystals or different trapped ions, for example, and this is very, very hard to do. While Xanadu has already a distributed quantum computing cloud up and running.
Another one is the ability to network. So the end goal is to have a large data center that can have smaller quantum computers that are networked together. Most companies, I think, will have to have some form of photonics in terms of the networking side of things, regardless of how they process their qubits. So our idea from day one is, well, if that's the case, why not keep everything photonic? And the ability to scale up, which is the networking or interconnects, comes more naturally with our photonic-based approach.
And this is a huge milestone on the quantum computing roadmap. And now the future of quantum doesn't look cold, it looks bright. One of the main challenges is optical loss. Loss of light during the computation, which results in errors which is very hard to correct. As a next step, Xanadu is focusing on addressing exactly this problem. Because, like in any quantum system, the goal is to keep the system as quantum as possible. And when it fails and the system decoheres, we're losing the advantage, the quantum advantage that gives us speed-ups. Every quantum architecture faces this, but it shows up differently. In photonic quantum computers, photons get absorbed and scattered as they travel through waveguides or fiber, and this results in the loss of light. And if too many are lost, the system starts to act like a classical computer, and we don't want that. And when they manage to solve this, we are yet to discover the most important applications of quantum computing that we can't yet even foresee. Richard Feynman famously said, "Nature isn't classical, and if you want to make a simulation of nature, you would better make it quantum mechanical." And it's a wonderful place, because it doesn't look so easy. Let's be honest, in the beginning we talked about this potential of quantum computing to unlock this exponential performance improvement. But to me personally, building a practical quantum computer is not so much about faster processing, but more about understanding of the fundamentals of the universe, figuring out things that we are not aware of yet. And this is a very exciting journey to see how this will unfold.
The practical quantum computer, everything you want, including our investors want true revenue. That comes with a quantum data center size quantum computer. So 1 or 2 acres of land with thousands of server racks networked together. We aim to build that in 2029. Where we are now, it's loss reduction. So we need to keep reducing the loss in the physical components. So that's our big focus. In fact, we've called 2025 the year of loss reduction.
Of course, other challenges remain that have to do with error correction, right? The whole industry is working on solving the error correction, and then quantum algorithms. This is a big, huge challenge indeed, but it's promising extraordinary rewards. And it's exciting to see that we are getting closer and closer to practical quantum computer operating at room temperature. Now, let me know what you think in the comments. I love to read your feedback. Let me know if this episode was too much technical. And now check out this episode and let this video to see some light. Share it with your friends, colleagues, and on social media. This helps this channel to grow a lot. Thank you guys. Love you. See you in the next episode. Ciao.